This is going to be another video on quantum mechanics. In the first video on quantum mechanics, we talked about the basic postulates and introduced Dirac notation. And in this video, we're going to review the model of the particle in a box. The particle in a box is going to be the simplest quantum mechanical model that you're probably going to encounter. And it can be used to model more complex systems, and in general, a system in which you have some particle trapped in a narrow region of low electric potential between two high potential barriers. Okay, so in a little bit more detail, we have a system in which we have a particle of mass m, and it's confined to a one-dimensional box. So, you can talk about the three-dimensional particle in a box model, but we're going to stick with the one-dimensional particle in a box for this first video. So the particle is confined to the box, and at the walls of the box, the potential is infinite, and the potential inside the box is zero. So we wrote V of x equals 0 inside the box, so from 0 to L. And then V of x is infinite outside of the box. So if 0 is equal to or greater than x, and if x is greater than or equal to L. So because of the way we defined the system, the particle will only have a kinetic energy term, and the Hamiltonian will be written negative h bar squared over 2 times m for mass multiplied by the second derivative with respect to x. And the Schrodinger equation for the problem is the Hamiltonian multiplied by the wave function is equal to negative h bar squared over 2m multiplied by the second derivative of the wave function with respect to x. And that's equal to the energy multiplied by the wave function. And also we require that the wave function is an eigenfunction of the Hamiltonian. And so the wave function must be a function such that taking its second derivative gives the same function. In this case, we can say that psi of x is equal to a sine kx plus b cosine kx. Then we can also write psi of x is equal to c e ikx plus d e negative ikx. To evaluate the constants a, b, c, and d, we use the boundary conditions, and the constant k is the frequency of the wave functions, which is also going to be determined by the boundary conditions. So now we have the Hamiltonian times the wave function is equal to negative h bar squared over 2m d squared dx squared multiplied by a sine kx plus b cosine kx. And then we're going to end up with the energy being equal to h bar squared times k squared over 2 times the mass. And remember, we know this about the energy because the Hamiltonian is going to be the operator and the eigenvalue is going to be the energy. So the wave function is the eigenfunction, the energy is the eigenvalue, and the Hamiltonian is the operator. And now we want to determine the constant k. So we know that the particle can't be at x equals 0 or x equals L. So the probability density, which is the complex conjugate of the wave function multiplied by the wave function, must be 0 at the values of x, or those values of x. So now we plug 0 into our wave function, psi of x, and we get a sine of 0 plus b cosine of 0 is equal to b, which is also equal to 0. And we now have that psi of x is equal to a sine kx, because we know from the boundary condition that b is equal to 0. Okay, now at x is equal to L, we have psi of L is equal to a times sine kl, which is equal to 0. And we remember that if we have sine of n, where n is a whole number, so, like 1, 2, or 3, and then we multiply that by pi, so n pi, if we plug that into sine, that's equal to 0. So we can say that psi of x is equal to a times sine n pi x over L, where we have that k is equal to n pi over L. Now we're going to normalize define constant a. We write the wave function in brackets, and that's equal to the integral from 0 to L of the complex conjugate of psi times psi d tau. And then we write that that's equal to the integral from 0 to L to a squared times sine squared n pi x over L dx, which is equal to 1. And then we get that a is equal to the square root of 2 over L. The normalized wave function is now psi of x is equal to the square root of 2 over L times sine n pi x over L. And the energy levels for a given value n are going to be h squared times n squared over 8 times ml squared. And the energy difference between each energy level is going to be En plus 1 minus En. Okay, and if you graph the probability distributions for the different energy levels, then you get roughly for the first three what I've drawn here. And in the ground state, the particle has the highest probability towards the middle of the box and reaches a minimum as it approaches the walls. At higher states, you'll see nodes, which you're going to see within the box where the probability is equal to 0, even though the potential is still 0. So you can see something that's different from classical physics and quantum physics, because the kinetic energy is going to be the only term. There's no potential energy inside of the box, but you're still going to have nodes where the probability of encountering the particle is going to be 0. So I hope this video was helpful. This is meant to be a review, not really an in-depth look at this model and at this problem in general. Just a review, so if you've already looked at a more rigorous treatment of the particle in a box, this should be a nice refresher.